Hello, in this video I'm going to talk about linear approximation and differentials. So we consider this graph that we have like y equals f of x, and what we want to do, for instance, is try to estimate any value along here. So what we can do is just consider any x along here. So maybe we can choose this one right here. We have x. And then we can choose another one, for instance. So maybe like just x plus h. Okay, now what this means is that basically we have to look at the line that passes through them. But let's do it like this. Okay, so I know that, for instance, that I can form my tangent line, or let's just even say just like the secant slope, for instance. So we know that we have this line right here. Now that's pretty close as it relates to the tangent line. So in this case, like, we know that we want that tangent line to lie alongside at x. Now, to do this, what we'll do is we'll just look at the distance from x to x plus h, and also the distance from here to here. So what that means is that essentially we're just going to form the ratio of the change in y over the change in x. Well, the change in y is really just the f of x plus h minus the f of x. And remember that the goal here is to basically just get that line that lies tangent to the graph. So we have that this is divided by x plus h minus x. But this simplifies down to f of x plus h, and this is going to be minus f of x all divided by h. Now, in essence, based on notation, delta x is really just the h. So in any case, we do have that most notation will just say that, okay, this is the same thing as f of x plus delta x minus f of x. And we'll put it over here that delta x is equal to h. And this is all divided by delta x. So I know that basically if I take the limit as my delta x tends to 0, that essentially this is just going to give me the derivative. So it just gives me f prime of x. So what this does is it allows me to basically just kind of figure out that this is the slope of our tangent. So we know that this is our slope of our tangent. But here's what we're going to do. Okay, so what I'm going to do is I'm actually going to pick a point alongside here. It doesn't have to be necessarily x. We can actually just change it to a if we want to. The reasoning behind that is because I need to be able to estimate anywhere alongside the function f of x. So what that means is that I'm going to pick x to equal to a. Then from there, we're going to have that the slope of the tangent is equal to f prime of a, and that the ordered pair that we're going to look at is a comma f of a. So this gives us an equation of a line. It gives us the following equation of a line that says that you have L of x is equal to f of a plus f prime of a multiplied by the delta x, which in this case we're just going to put x minus a. Okay, so here what happened now is that basically this is what we call the linearization of a function at a point, and we call it x equals a. So here we're just going to say that this is the linearization at x equals to a. So to kind of understand, what we just wrote down, basically what we're saying is that as delta x tends to 0, we have that the linearization of x is going to be approximately equal to the function f of x. So that's actually pretty useful in this sense. Okay, now how useful that could be? Well, imagine if you were trying to estimate like perhaps like the square root of 122. Well, I know that, what the square root of 121 is, it's just equal to 11. And then I know that basically that the delta x in this case is equal to, well, 1, because you have that there's a change going from 121 to 122. So what this means is that basically you can probably approximate the square root of 122 using the fact that f of x is equal to the square root of x. Then just use that f prime of x is equal to 1 divided by 2 root x. Now, in this sense, yeah, it's getting a little far ahead, but that's essentially is the goal, is to be able to estimate, you know, values of which that we do not know necessarily. But keep in mind that I wouldn't necessarily try to estimate the square root of, let's say, 145 using 11. Why? Because it's too far away. The delta x is too big. Delta x being 1 unit is okay. It's not great, but it's probably the closest that we can get. So let's try to do the linearization of the square root function at x equals to, I think what we're going to do is we're just going to use x equals to we can use just 1. Okay, so here we just need to basically just find f of 1. So f of 1 is equal to the square root of 1, which is just 1. So that tells me that we're at the ordered pair 1 comma 1. Now I need to find a derivative, which the derivative of the square root function, because it's equal to x to the 1/2, that's going to be 1/2 x to the negative 1/2. But when you plug in the value 1, you're going to get just 1/2. So this tells me that I can go ahead and say that the linearization is equal to, well, we have 1 plus 1/2 multiplied by x minus 1. And if we go ahead and we simplify this, this is going to give us 1/2 x plus 1/2, which is equal to just, you can say like x plus 1 divided by 2. Okay, so we have that this is our function for the linearization of the square root function. Now, that means that basically that we can kind of estimate anything that we want. So for instance, if I wanted to estimate, let's say like the square root of 1.1, well, accordingly, this would be equal to L of 1.1, which is equal to 1.1 plus 2 divided by 2, not 2, that's supposed to be 1. Okay, so that's going to be divided by 2. So this is going to be 2.1. So we have 2.1 divided by 2. And of course, like once we do this, this is basically telling us that this is equal to 1.05. Okay, now in the event that you want to use your calculator, I mean, we can, like 1.1 plus 1 divided by 2, 1.05. But what I want you to do here is take a look at the value 1.1 and take the square root. So you see that basically we're off by a little bit in this case. So like, we have 1.05 minus the actual answer. And we find that basically we're off by 0.0119, which is not very much, and it's very close in this case. So we have that the error is equal to 0.00119. Okay, but notice that if you did square 1.05, so like if you took like 1.05 and you squared it, notice that you would get, let's see, 1.05 squared, you get 1.1025. Which means that, yeah, we're off in this case, but it's very close at least. Now, notice that you would not necessarily use, let's say, for example, like the square root of 3. So, like, if you used, like, that you were estimating the square root of 3 and you used your linearization of your function, basically you'll note that in doing that, you have that that's going to be 3 plus 1 divided by 2, which is 4 divided by 2 is 2. Okay, but that's completely way off because in this case, if you look at the delta x for this one, the delta x for 3 and 1 is basically just 2. This is way too big. So we have that this wouldn't work. And you note that if you square 2, you get 4, which means that you're off by 1 unit in this case, which is way off from what the square root of 3 is, because you have that the square root of 3 is 1.73. So in this case, you wouldn't use root 3 with this linearization because it's just too far. So now, the thing of which that we can work with in terms of linearization is that as long as we are close enough, then in this case we can always use the function. So like let's say that we have that there's an equation of which that you have, let's do an easy one. So let's say that we have x squared plus 4x plus 4. And yeah, so basically, let me just go ahead and change this a little bit. So I want to find the L of x for g of x, and we'll just say at, we'll just say at x equals to 2. Okay, so this means that basically that you would have to figure out, like, first off, like, what is g of 2? So g of 2 is equal to 2 squared plus 4 times 2 plus 4. Okay, now this gives us basically like 16. So we have that that's going to be 16. Okay, now what if I wanted to go ahead and then find, yeah, we're going to go ahead and find the derivative. So we have g prime of x is equal to 2x plus 4. But we need to find the slope of the tangent. So g prime of 2, this is equal to 2 times 2 plus 4, which is basically just 8. So we have the slope of the tangent is equal to 8. Okay, so what this means is that we can go ahead and formulate our equation L of x. So L of x is going to be, let's see, we have 16 plus 8 multiplied by x minus 2. Okay, so we have x minus 2. And this is going to give us, let's see. Okay, so it looks like the 16 is going to cancel out, and it's just going to give us 8x. Okay, so we have that it just gives us 8x. So now, let's say that we wanted to figure out what g of 2.001 is. Okay, so if we go ahead and we try to find 2.001, well, note that basically we figured out that as long as it's close enough to the center point, then in that case, we don't need to plug it into here. So we have that L of 2.01 is equal to 8 multiplied by 2.001. And what this gives us basically is just 16.008. Okay, well, that's not too bad. So let's see. And again, if you want to use your calculator, you can. So like 8 multiplied by 2.001, and you get 16.08. But the good question that I might have is, how off are we? So we can go ahead and do that. So like, let's say that we did 2.001 squared plus 4 times 2.001. And then we do, that's plus 4, right? So that's plus 4. Okay, so we just hit enter. And we actually are close, very close. We're only off by, let's see, well, you can kind of see that basically if you take the difference of the two, that we are off by 10 to the negative 6. So the error is equal to positive 10 to the negative 6, which is very good. Okay. Now, this only was because of the fact that the delta x was equal to 0.001. Now, note that basically we can actually apply the linearization also to, like, just this one right here, x squared, and then just this one right here at 4x, but technically 4x is already done. You don't really need to find the linearization of an equation, like of a slope times a coefficient x. But I was noticing that when I was plugging it into here, I could have technically estimated even this right here, and then try to see what I get, but it's actually going to give you the same thing, like if you do that. But it's kind of interesting that you can apply linearization to basically the whole thing. or individually. Now, the thing of which that we have here is that let's go back to the derivative function. So we have f prime of x. F prime of x is equal to the limit as h approaches 0 for f of x plus, we can do delta x minus f of x divided by delta x. Now, what I can do here is, like, maybe we should just change this a little. Okay, so I have that basically this is the delta x, and that's going to 0. Now, what I can do here is basically say that, what if we were to multiply by delta x on both sides? Well, if we were to multiply by delta x on both sides, then what we would end up getting is that this would give us that you now have that f of x plus h, or delta x minus f of x, is now approximately equal to f prime of x times delta x. Now what that means is that essentially we have that the change in y is approximately equal to f prime of x times delta x. But notice that essentially, if you look back at the derivative function, it's mostly the same thing. Like saying that the average rate of change is going to be approximately equal to the derivative. Okay, so that's really all that this is saying when we look at this. So we have that this is going to give us the change in our y. Now, in the way that I kind of learned it was that, I looked at it like this, where I know that I can essentially just estimate using this alternative notation, saying that we have f of x plus f prime of x multiplied by delta x. So it's more or less the same exact thing. So what that means is that I can go ahead and use this formula to find things like the square root of 5, for instance. So, like if I was to say, well, let's go ahead and find the square root of 5. Well, basically I would have to choose, like, what is x, what is delta x, and so on. So, well, we should just say that f of x is the square root of x. So I know that f of 4 is equal to the square root of 4, which is equal to 2. That means that I know what x is. X is equal to 4. But if that's the case, then that means that delta x is equal to 1. So what that means is that we can go ahead and find f prime of x, which is just 1 over 2 root x, and then we can find f prime of x, not f prime of x, it should be 4, which is equal to 1 over 2 times the square root of 4, which is equal to 1/4. So essentially we have everything that we need as it relates to finding the the approximation for the square root of 5. So that tells us that we have the square root of 5 is equal to, well, not equal, it's approximately equal to 2 plus, well, we have that we're going to take 1/4, and we're just going to multiply that times the delta x, which in this case is just 1. So this gives us that the square root of 5 is 2.25. Now, if we go ahead and we look at that, well, note that basically 2.25, if you square it, you get 5.0625. So it's definitely off, but you know, we didn't expect that it would be close, really. 5.0625. So if you look back at the square root of 5, though, you'll see that it's 2.3606 and so on. So yeah, we're kind of off, but there are better ways, but we don't really look at it in this class. So 2.23, let me see, 606, and it kind of just keeps going. Okay, so this is our actual estimate for this, but if we were to round to the nearest 1/100th, then in that case, it wouldn't be off by very much. Now, in any case, like we can actually refine this if we wanted to, because now we have a better estimate, the 2.25. So if you want to use 2.25 as a better estimate, you probably can, but it's a little tricky. Okay, so more or less, you're just expected to kind of just know like how you can use differentials to estimate quantity values. So, for example, I would say go ahead and try to find a tangent of 46 degrees, or maybe try finding cosine of 62 degrees. You'll notice that basically that it's going to be close to 1 for this one, and this one is going to be close to 1/2. Okay, so try those. Now, last but not least, the things of which that we do look at is, for example, okay, so notice that we looked at the change in y over the change in x, and that we said that that was approximately equal to the derivative. Okay, now if I was to basically just apply the limit operator to both sides, like if I take the limit as delta x tends to 0 on both sides, so like this would be, this is delta x, so this would be equal to dy over dx. So this tells me basically that that we have that dy dx is equal to f prime of x, which essentially means that we can go ahead and say that the dy is equal to f prime of x times dy, or dx, sorry. Okay, so we have basically kind of like another formula in a sense that this gives us that we can estimate the change in y. So that's the only difference between these two. Okay, so this represents basically the change in our variable y. So what that means is that essentially, if we were to consider a circle, like if we have an area, usually let's see. Okay, there we go. So if we have that, we just go ahead and we say, well, this circle has a radius r. Well, I know that the area of a circle. Okay, so the area of a circle is pi r squared. Now, imagine if I had that, we had 1 inch as our radius, and it went to 1.1 inches. Well, what if I wanted to find the change in the area? And this is very, useful for whether I'm trying to cover a garden with soil and just estimate how much additional will I need versus if I were to make uh, if I was to make a sphere much larger, then I can estimate how much more paint I might need to cover it entirely. So in this case, like I can find the change in R. So we can say that, well, dr is equal to uh, zero point 0.1. So we have, let me just do this again. We have that it only increased by zero point 0.1 inches. But what this means is that we need to go ahead and find dr, so, or dA. So the area is going to be 2 pi r. But remember that chain rule says that, yeah, we're just going to put dr. Okay, so in this case, if we want to find the change in the area, you're going to have to substitute basically the value 1 inch. So you have 2 pi multiplied by 1 multiplied by zero point 0.1. Okay, well, in this case, like if we go ahead and we multiply through, so we have 2 times the zero point 0.1, which is obviously 0.2, and then we just need to multiply by the pi. So we have pi, and that equals 0.6, 62831 or 832. Okay, so this is going to be, okay, so um, if we preserve the pi, it's going to be 0.628, actually, what I meant to say was the zero point 0.2 pi. Okay, but this is approximately equal to 0.62832. Okay, so that was the approximation in the change in the area. Now, most students, they tend to say, well, if I wanted to find the change in A, why don't I just do 1.1 1.1 squared multiplied by pi minus, well, in this case, it's just minus pi. So this is going to equal to 1.1 squared minus 1, and that's multiplied by pi. And okay, well, 1.1 squared is like 1.21, so let's see, 1.1 squared minus 1, 0.21. Okay, so that's going to be 0.21, so 121 pi. And notice that if you go ahead and you find the approximation, well, it's not going to be off by too much, but so, well, symbolically it was not off by too much, but now we see that that's going to be 0.65973. Okay, so this is actually, it's a little more off than expected. 6593. 973. Yeah, yeah, yeah. Okay. Alrighty. Okay, so 973. Okay, so what that means is that, that yes, it's more practical to just go ahead and take the difference of the two, but it's a lot faster in a sense to just use the approximation because that's the whole point of it. Now, last but not least, I know, yeah, this is how you would use it with applications, but in our case, like sometimes that we might give you a function of which that you would use, the notation. So again, we know that the change in y is equal to f prime of x multiplied by dx. So suppose that you wanted to rewrite a function in terms of its differential. So we just say like find dy for g of x equals to Okay, so let's say like you have x divided by x squared plus 4, and we'll just do 2x. Okay, so in this case, like all that you would need to do for this one is you would need to find the derivative, and then that's it. So in essence, we're just saying that dy in this case is equal to g prime of x times dx. So all that we need to do is just find g prime of x. So g prime of x, well, unfortunately, you have to use quotient rule. So you have x squared plus 4 squared. Then you have x squared plus 4 multiplied by 2 minus 2x times, well, in this case, it's just 2x. So here, you're going to get 2x squared plus 8 minus 4x squared. And all of this is divided by x squared plus 4 to the second power. So this equals to, let's see, 8 minus 2x squared, all divided by x squared plus 4 to the second power. So here is the derivative, but remember that we're asking for what is dy. So dy is equal to 8 minus 2x squared divided by x squared plus 4 squared multiplied by dx. So essentially this tells us that we can estimate the change in y by using the form of which we rewrote our function. Okay, and this was just using quotient rule. Now you can go ahead and try like different examples if you want to, but in any case, like it's all the same. You're just rewriting it like with the derivative times the dx. Okay, and then note that this is nothing fancy because it's just saying that you have that dy dx is equal to 8 minus 2x squared divided by x squared plus 4 squared. So, whenever you see that you want to solve for dy, just think of it as just finding the derivative.